Well, welcome to the Water Resources and IWRRI Seminar Series. Today it's my pleasure to introduce Neal Farmer as our speaker today. He holds a BS from the College of Southern Idaho and an MS from the University of Idaho, and he's got many decades of experience and study looking at the Hagerman and some of the springs in Southern Idaho that I'm really glad he's going to share with us today. So take it from here. Thank you, Neal.
Thank you, Robert. Thank you, everyone, for your time and attention. I think we've got some good information to provide today to folks. Just a little audio video test. I assume everybody can see a rainbow on your screen and can hear me all right. Is that correct from anybody? Okay, got a thumbs up. Great. So this is a continuation of information and data that's been gathered since about year 2008. And one of the reasons is this geologic contact is a major hydrogeological control of how the springs issue from the East Snake Plain Aquifer in south central Idaho. I do have a Google Earth file with pins of all these springs. We didn't get that out to everybody prior to the presentation, but I do have, of course, a map. But if you do want that Google pin file, let Robert know, and we'll try and get that to you as soon as possible. On your screen, you'll see a surface, and it's the geologic contact between overlying quaternary or young geologic sediments and underlying lower permeability sediments. And it has some major controls for how groundwater moves. And so the next many slides, and I do have quite a few, I'm going to try and push through them as fast as possible. And we might try and hold, usually I like questions during presentation, but I've got so much to get through, we may have to hold them until after the presentation or chat session or something. This is the study area in south central Idaho. That's near the towns of Gooding, Wendell, and also Bliss at this location. All these red dots are control points that are used in the 3D model of the QT surface. I'll get into that acronym here in a second. And 86% of these control points are within 2 miles of a mapped outcrop. The series of slides will start up in the Niagara Springs area, travel down the Snake River Canyon, and touch on a number of springs, not all of them, but a number of them, through the canyon all the way to Bancroft out here to the west. And the modeled area is this stippled line area. And then this is overlaying on just a colorized NED or DEM map. The model used 86 contacts mapped by a number of different entities and 123 ground truth well drilling logs, and 73% of those were GPSed. 86% of them are within 2 miles of a mapped QT contact. We'll get into the QT in just a second. Along with 19 springs that have been all mapped, ground truth, and GPSed on site, for a total of about 229 control points. Some of our methods were just foot surveys, hand augering, literally track hose, excavations, roadwork exposures, fossil examinations in outcrops, and we combined that with the well drilling information, entered that into Rockware software and Surfer software to create the information and produce a surface, subsurface, and then used that to evaluate against Harold Maldy and Harold Stearns and geologic mapping, as well as water table mapping, groundwater chemistry, and groundwater tracer tests to see how close it matches. And we also used high accuracy, vertical accuracy GPS and laser transit. There's been a lot of studies starting since about 1900, and Israel Russell started in 1900, and then Harold Stearns in the 20s and 30s, Howard Powers in the 50s and 60s roughly, and these are just general time periods. Covington, Whitehead, Weaver, and also Harold Maldy, all covering different time periods, and these are all USGS scientists. Superficial mapping by the same entities as well as Idaho Geological Survey, Virginia Gillerman, and others. And then key reports listed here that discuss and describe this geologic contact and formations. Israel Russell issued a report in 1902 and by the USGS, and one thing that's kind of interesting to me is he labels it as a geological reconnaissance and not a detailed survey, but then he wrote an over 215-page report with actually a lot of detail in it, so it was kind of interesting. But he was wondering back then if this lake bed deposits disappeared under the lava flows in the presence of the central and eastern plain. And he even wrote a section on page 29 about the possible eastward extension of tertiary sedimentary beds and how they may extend underneath the basalt flows on the eastern Snake River Plain. And then Harold Stearns came in 36 and he put some more work to it. Russell kind of identified it and theorized it. Stearns came in and did some more work and identified the processes involved with some of the canyon filling lavas. So we had ancestral canyons that were carved into these older rocks and sediment, and then later filled with more younger, more permeable basalts, and there's numerous displacements that occurred. He put forth a model where you would have a cut valley that filled, and then another cut valley, and it would push that Snake River further and further south. That's why the Snake River is located on the south boundary and not central to the plain as most rivers. And that those valleys would fill from volcanic eruptions of basalt flows into those valleys. Harold Maldy came in and did he was, in my opinion, a heavy hitter in defining these paleo channels and canyons, and started mapping them out. Stearns identified the processes and some of the locations, and Maldy started mapping those out, and the sequence of which. So in one of his publications, he has like canyon number 1, 2, 3, 4, 5, and map those out. Interesting to some degree is Maldy was drafted in the Navy in 1942. He was going to be a pilot and lost his eye. And then he went to college and got his degrees and did his entire geologic career with only one eye, which is pretty amazing. He died in 2007, but he was a real heavy hitter. And these channels, we're going to look at these number 2, 3, 4, especially in this presentation. Whitehead and Lindholm in 1985 with the USGS, they came in through the RASA project and drilled some deep wells. This is a 1,000-foot well where they actually identified specific geologic formations in that well. So that's one of a key control point for the modeling purposes. So really what we're looking at is the contact between younger Snake River group and older Idaho group rock formations, but it's generally the quaternary tertiary boundary at this area. And the younger rocks, the Snake River group, are highly conductive of the aquifer of the Snake Plain and host the aquifer. The older tertiary group rocks are typically lower permeability and create an impermeable boundary. Lake Idaho was about 150 miles long, extended clear, mapped well in theory and mapped in this publication to almost Jerome area and Twin Falls in this blue area. We're going to look at this area here. There was a sequence of caldera events, volcanic fields that occurred across southern Idaho, which is now underneath Yellowstone. And the Twin Falls area one occurred about 13 million years ago. Lake Idaho is about 5 to 1.5 million years ago. And so this, again, just a reminder, we're now going to start a sequence of fun photos, let's say from Niagara down along these springs to Bancroft. And so valley filling basalts, some of the characters of valley filling basalts is when the QT contact, quaternary tertiary contact, is very low in elevation, you get very high cliff faces. And here we have blocky quaternary basalt, younger basalt, deposited on top of bedded brecciated pillows that filled an ancient canyon. That's about 80-foot cliff face right there. And down at Niagara Springs, the QT contact is very low, so you get a very high wall in the canyon, and the talus slope is a little bit lower. And then on the left, conversely, is a high QT contact, where you have a very short cliff face and a very long run out of talus. And these are the brown tertiary basalts. They tend to be brown, more dense, and then the overlying more gray colored quaternary younger basalts. And as you can see in other slides, these tertiary sediments and basalts tend to almost have a convex weathered surface or profile in the canyon wall. And we'll see that in some other photos. And we move up to Clear Springs grade a little further west. There's a nice exposure in the road cut of the underlying brown tertiary basalts and the overlying gray quaternary basalts. And there's a nice contact here that we've mapped with laser surveying equipment with Idaho Power support and National Park Service support. And then map that contact that dips about 10 feet in the exposure to the north. Again, down in this area of Clear Springs, we have tertiary basalt exposed. The QT contact is high in elevation in this area, so there's a short cliff face. And typically few to no springs where the QT contact is very high, and typically few or no pillows exposed either. A little further west of Clear Springs is the old Clear Springs grade. And here again, very short quaternary geology on top. And this is the tertiary basalt underneath, and they weather much differently. So we start looking at the model and comparing them. This outcrop is located at real high QT contact, and this outcrop here is located at real low QT contact. And Clear Springs is located in a low, and Niagara Springs in a low. We'll look at Manberry Springs and Blind Canyon and Box Canyon here in the next few slides. Blind Canyon Springs has a contact exposure of the Glens Ferry sediments. They're tertiary, so you can have tertiary lake sediments or tertiary basalts, both of which are low permeability typically. And this is the bottom of the aquifer for the ESPA at Blind Canyon Springs that are issuing out. Fairly high cliff face here. This is kind of a medium elevation along with some fossils that came out of that exposure. Box Canyon also has a QT contact in the foreground as tertiary basalts with some tephra material underneath. And if you look up the canyon to the east here, if you notice on the right side of the canyon, there's a lot of springs discharging or issuing from the talus and thus the green vegetation. Conversely, on the south side, essentially no springs are issuing from the talus except down along the base. There's a few at the river level. So it says that that contact is dipping from right to left in this photo. And that contact continues over to the Blue Lakes, Blue Heart Springs rather. This is a valley filling basalt, again, real high cliff face. And then over here, it becomes a very short cliff face of the same basalt because it's resting on top of the tertiary contact. So we have the QT with very short height in the cliff face. and Blue Heart Springs issues from down low, actually below river level at this location. So these valley filling basalts really become evident from henceforward. At the top of Blind Canyon grade is, here's a 3D model with some photo correlations, is located right here. This is at land surface where Glens Ferry Formation that crops out, creates a high, and Blind Canyon, Glens Ferry sediments located in this area, and Box Canyon creates a low in that QT contact, and that's a lot of springs and discharge area in that area. We're looking to the east, and there's no vertical exaggeration on this plot. But this plot is 2 times vertical exaggeration. And we'll take a look at, here's Harold Maldy's canyon filling route number 4, which matches our modeling efforts of the low QT contact. And also this is about 2.5 miles distance between Break Spring and Blue Heart Spring, just for some scale. We're again looking to the east. But I wanted to point out this area in here where you see kind of a flat area along with some rises in that QT contact. And when we add the 2013 water table map of the ESPA, it also creates basically a peninsula that flattens in the contours, gradient flattens in this area, kind of a table feature. And so we did a dye tracer test years ago from a well back here at about 3 miles distance. And that dye traveled west to Banbury Springs and Break Springs, but it split. And it wasn't until we started looking at subsurface geology that we gained some evidence that the reason it split is because we had a high QT contact of low K permeability that influenced the split of that dye tracer test. We also have a little 1/2 mile trace over here at Clear Springs. These are projected in 3D. And then we had a couple of little isolated hits of fluorescein dye over in Box Canyon. It'd be nice to repeat that trace and try to confirm that. Harold Stearns in 36 identified this canyon filling basalt, which means a low QT contact. That was in Maldy's route number 4. This is an air photo of that canyon filling basalt in here. And on the bottom, you can see a little profile of the exposure of that canyon filling basalt. The tertiary sediments are located over here to the left, brown basalts, and the quaternary high permeable, more recent basalts that filled that canyon are located here. And then Dave Blue took a trip to Kansas, and he texted me, he said, I found the QT contact in Kansas back here on the lower left. So we'll just keep mapping that. We moved to Thousand Springs. Thousand Springs has structural control in addition to sedimentary control and bedding control. And so you can see the dipping of tertiary bed sediments right here above the springs. These are some more of the dipping sediments here. And then behind the Thousand Springs power plant, you can see the dipping sediments exposed, the tertiary older stuff with the quaternary younger basalts up above. Russell in 1902 identified this feature up here on page 165. And this is the dipping beds that Russell was identifying here, where the basalt is dipping into the Hagerman Valley. And then if you notice up here on the skyline, there's some more horizontal basalts up here. So if we look at that on a 3D image here of the ground surface, this is the Thousand Springs complex, which is probably a fault-related structure, maybe a hinge fault or a fault associated with monocline that's mapped on the south side of the river. It could be a relay ramp structure, but something has caused that block to fall, and groundwater as well as lava flows are both following down this ramp or tilted bed structure, and then daylighting out as Thousand Springs. The groundwater gradient we've mapped right down that ramp structure also. Then we move back to the background where there was horizontal basalts. We're kind of back up on top to Curran Tunnel. Stearns in 36 identified this location as also eroding into possible lake beds and sediments, and the effective base of the ESPA aquifer is at this elevation of 3150 underneath our lake bed sediments. and on the order of 300 feet thick in this area. Typically blocky basalt that overlies the brecciated pillow zone, which then will lie on top of the tertiary sediments. In this image, this is beta grade nearby. In the background over here are 600 feet of Glenns Ferry tertiary lake bed sediments. In the foreground here at beta grade on the east side of Hagerman Valley, there's a number of homes in this area, and they have drilled wells through about 62 feet of cap quaternary basalt and then into tertiary sediments that are on the order of 300 feet thick. And then their wells are open in basalts, tertiary basalts underneath these sediments, so quite deep. They had to go deep to get water in this area. We found fossils, bivalves, willow leaves, and otter coprolites in this outcrop. And that outcrop is located right here. And you see these number of control points, all kind of grid space. That's because homes are built on that. That's at land surface and beta grade located here. Current tunnel is issuing from a low in the QT contact, and there's a number of other low areas in the QT contact where other springs issue out or break over, basically a pass or saddle in the QT contact. So that brings some information for a cross section put together. This is the beta grade again. These are a bunch of those domestic wells that penetrated 62 feet, 300 feet of Glenns Ferry sediments, and then terminated in underlying tertiary sediments. And then there are other wells that are just shallow in just the quaternary basalt. And then east of that is a USGS well, 600 feet deep. They penetrated a couple, this is not to scale, 200 feet of Glenns Ferry sediments and overlying quaternary basalts. And then the well that Whitehead and RASA program drilled about 8 miles distance also penetrated about 175 feet of Glenns Ferry formation sediments, as well as quaternary sediments and other deposits for confirmation of that. So you can see 600 feet on the west side of the valley, and it's thinning eastward. And this probably extends into the Jerome area and causes a major hydrogeologic boundary in the vertical sense of the aquifer. The ESPA is flowing across the top through the quaternary. And so we have to be really careful about using wells in modeling exercises that are actually completed in this lower system, which has been done in previous years many times, and combining those water levels with wells from really the ESPA proper in this area. So, and that's supported by the geology, the hydrologic analysis for correlation, some chemical data from the USGS, as well as some temperature differences and stuff. So, and down in Hagerman Valley, we've got some artesian conditions. This is a westward looking model, land surface located here, greatly exaggerated, truncated, clipped water table map here and the QT surface, just showing how it rises up above the water table in places and of course down below in others. So if we move towards the north a little bit and towards Malad Gorge, this is Maldy's Canyon Route number 2, which matches our modeling also. And in addition, here's a bunch of these little small springs and some scale here is 4 miles distance across this area. This is one of the little small springs that comes out that's fairly high in nature along that QT contact. Frank Irwin gave me a call when he intersected that contact years ago. Sometimes there's tunneling in along that contact to enhance flow out of the aquifer. And Frank had a track hoe, and so that's also, it's pretty nice to have somebody friends with track hoes to expose and pull out nice blocks of samples of Glenns Ferry formation for that QT contact confirmation. And he also gave me a call when they were working on the Florence Spring tunnel, where they tunnel in. This is the overlying quaternary basalts and the underlying Glenns Ferry formation lakebed sediments right in the floor of this tunnel. And we exposed those and then penetrated them with hand auger methods for about 20 feet and then used lasers to survey in the elevations for control and GPS at this location. So we're at Malad Gorge now. This is Maldi's #2 canyon located here, and these are the bedded breccia and pillow basalts. There's a person standing here for scale. And this is, again, high cliff face where we have canyon filling basalts. And there's a nice little house down here at the bottom of the talus slope. And there's a nice outcrop of tertiary Glensberry Formation there at the mouth of the canyon. And a cross-section that was generated in 2011 shows how those sediments extend from the west side of the Hagerman Valley across the Snake River to the east, and a possible scenario for understanding those sediments as an aquifer tertiary contact with the QT. And so this is the location of that previous slide, Malad Gorge. And when you add the 2013 water table service, and I use the 2013 water table because it's a high resolution water table where we measured about 200 wells in a small area. And our other water table maps don't have that resolution. And so they don't show a bench feature in the water table in this area, which is right where Maldi's Canyon is at this location. So you see the flattening of the water table, if I back up, right in this canyon filling area. So we did some dye tracing here many years ago, a 3-mile trace that basically went right down the canyon to Malad Gorge, and another short trace over from this direction, which is also consistent with the QT model, along with the water table map and Maldi's mapping in this area. So this is a different perspective. This is from clear down by Bliss area now, and we're looking back. We started our springs, Niagara here, and Clear Springs, and Briggs, and Banbury, and the Thousand Springs faulted block area here, and some scale here for distances, and our groundwater traces here in green, and another groundwater trace over here at Banbury and Briggs in green. These this is Maldi's route #2 for Buried Canyon, and it matches our computer modeling of that surface, as well as some of his routes 3 and 4. And you notice how high the QT contact comes up at Bliss, which is kind of problematic in understanding some things down in that area. This is actually land surface. People are building homes right here, as well as up here to the north. And we're looking to the southeast in this image. So Maldi found a buried canyon, that ancient canyon that was filled with McKinney basalt, which is only 50,000 years old roughly. And this is the location of that canyon filling basalt with a lot of great thickness of brecciated pillows that go right down to the Bliss Reservoir water surface. This is the QT contact with the older brown colored basalts in here, and of tertiary age, and then the younger quaternary age of the McKinney basalt. And there's springs here because this is probably a losing section of the river, and there's probably the reservoir and river is actually leaking into, and this is Maldi's theory also, into this brecciated material into the groundwater system. This is just downstream from Bliss. I should have got a scale on this, but this is at least a mile in width here, I'm guessing. I should have measured that. But regardless, as we look at an earlier photo, I found this 1946 air photo from the U.S. Geological Survey. This is pre-dam, so the Bliss Dam had not been constructed, and you see the rapids in the Snake River, and that brecciated material in the photo, that's not in the PowerPoint because you can see it better in the raw photo. These brecciated pillow features appear to go clear down to the river level. So this, what that means is this Paleo Canyon, along with the Stearns Canyon we saw earlier, was deeper than the current canyon that is cut in the Snake River. And so this is probably a losing stretch where the river is contributing water to the groundwater system just west of Bliss. And this is the 3D model showing that low canyon area that we just saw right here. It's Maldi's Canyon Route number 5, which also is consistent with our 3D mapping in this area for this low area of the QT contact or an ancient canyon that's been filled by a basalt later in time. And then Maldi's route travels from that basically inlet of surface water to the groundwater system down to Bancroft. And that's about 10 miles distance from Bancroft Springs up to the Bliss area. And then right here, there's some other good contacts, the Bliss Dam Grade Road, which has Tuana gravel formation, which is part of the tertiary sediments, and the basically represents the draining of Lake Idaho, and the rivers are starting to flow in across the Glens Ferry Formation. And then the younger McKinney basalt, which is only about 50,000 years, sitting right on top of that. And this has all, of course, been mapped by all the entities that have been done mapping in this area. And it's located roughly here at this road grid. So Bancroft Springs, this is the last spring, the furthest to the west. Has really been a problem for a number of years, and really many individuals, including Maldi, really don't know what to do with Bancroft because it's a little bit out of character than the other springs. And it is a canyon filling basalt, the Kinney basalt, Quaternary age, pretty young, resting right on top of tertiary age sediments. And it's difficult to get into. The access is very difficult. And so many previous mappers and researchers probably did not directly on the foot access this spring area, but rather like this, tried to map the geology and contact from a distance. I would surmise anyway, and because one of the things Maldi states in his 1971 report on page F19 is that the Bancroft Springs, he basically says, will remain a mystery until some drilling penetrates and conceals the lava dam west of Bliss and reveals its character. And one of the reasons is because the discharge of Bancroft is oddly low. It's only about 17 CFS measured by Killstrom back in, I think, 71. And so it's like, well, if this is a real low QT contact and very permeable in the base, how come, we don't have a Niagara Springs or Clear Springs or these large discharge springs coming out at Bancroft, and why is it just a piddly little 17 CFS? And so it's a tough one to deal with. This photo was taken back in 2008. Some of these individuals have retired or moved on. But in 2021, Idaho Power provided opportunity for IDWR staff to go in and take a look at Bancroft Springs. And so I took them up on that offer and couldn't get anybody else to go. So we got some direct on the ground access to Bancroft, and we were able to identify some good information. We did measure some flows at 19 CFS, which is about what Killstrom measured in 1971. These are some Glens Ferry sediments, lake bed sediments, tertiary age, right around the corner, really, just a couple miles to the south of Bancroft. And then some tertiary basalts that were mapped also that are right next to Bancroft. And so the tertiary is exposed around Bancroft. And then so Dane Bates with Idaho Power and I were there measuring some flow rates in a jungle and and he found an outcrop that has not been mapped by anybody, and it's Glens Ferry lake bed sediments of the Glens Ferry Formation, tertiary age. It's deep in the stratigraphy, so this is pushing probably on the order of 5 million years old. And here he is pulling out some nice carbonaceous paper shale units from Bancroft. And of course, we took a closer look at those sediments and explored the character of the outcrop more and GPS that. And that means that the effective base of this aquifer is at the moment the best that we can determine at 2538 elevation. This is above the Snake River. And so all of the spring water is issuing across this dense silty clay upward finding floodplain facies of the Glens Ferry Formation. This is some more photos of the carbon fossils, and it should be rich in pollen, and we're trying to get some analysis done for some pollinology to see what we can do. When it dries up, it cleaves out and literally kind of paper layers, and that's why they call it a carbonaceous black paper shale capping, which typically caps upward finding floodplain units with silty clays underlying them. No biggie, just a little video, water pouring out, and some of the sediments exposed here.
Yeah, go for it.
And Dane's just trying to show some layering and sedimentology underneath the waterfall. No biggie. So one of the problems we have with Bancroft Springs here in the lower left is, how does water get to Bancroft? And if it is river water, is it solely river water that's making its way through a buried canyon? And we don't have any control for the QT contact at this location, so it's possible that canyon or low extends right through this saddle down to Bancroft. And so maybe that's the source of water to Bancroft. And so Idaho Power has supported collecting some water chemistry samples. So we're looking at some water chemistry to look at fingerprints, chemical fingerprints of this spring compared to river water or the ESPA water from over here. And we're in progress of that. And nobody's really ever measured Bancroft, so we don't really have any hydrographs that we can look at. And there's very few wells between Bliss and Bancroft, but there are a few. So in this image here, you'll see the QT contact without contour lines. And then the 2018 East Snake Plain Aquifer water table map with contour lines. And you can see how up towards Bliss, it is cutting quite deep underneath these sediments through the lake bed sediments essentially. And at Bliss, there's 500 feet of a complete exposure of the Lake Idaho Glens Ferry sediments. The Tuana gravel lays right on top of this ridge, and they're coring it out for gravels. So we have the complete deposit of in excess of 500 feet of lake bed sediments that extend down through this vertically. So if the ESPA is making its way through sediments completely, then it could be. Or are we getting a combination of ESPA water and Snake River water, which is making its way on down? Or is there another canyon and we don't have control points right at this saddle? Is there another buried canyon of basalt, and therefore the ESPA is traveling through basalt all the way on down to Bancroft? It's a good question, and nobody really knows for sure. But it is problematic in some of our mapping because if the ESPA is traveling or flowing through 500 feet of silty clay lake bed sediments, you would think we would see some tightening of the groundwater contours if you embrace the Darcy equation for that. But we don't really have any control for groundwater contours. And so if we want to extend this ESPA water table map from Bancroft to Bliss, we really need to get some groundwater measurements for control in between. And so at this point in time, it's my sense that Bancroft Springs is not part of the ESPA, and that there's more evidence that supports that it's not part of the ESPA system and therefore not part of the model domain in this area, and that we really need to take a hard look at investigating this area better to include it or exclude it from modeling exercises, and also understanding Bancroft Springs more in its character and whatnot for other reasons like endangered species and stuff like that that are in the canyon. So I think with that, I smoked right through it, and I think I even got done faster than I thought I would. And if there's any questions, feel free to fire away.
All right, thank you so much. What a puzzle, and what a dream for a hydrogeologist to work on. And we actually do have a question in Moscow.
Yeah, I was wondering about the groundwater ages of the springs, if you could elaborate it on that.
I had to turn my volume up. Could you repeat that question?
Yeah, I was wondering about the groundwater ages of the springs, if any samples, any like age dating samples were collected. There's similarities or differences between springs as you move down the state.
I think there has been some age dating of the water. We're not currently looking at that yet, but we do want to look at that. I'd have to defer to somebody else that may be listening that might have more information about age dating of the water. I do know that our groundwater traces, not all of them are shown here. This is a 3-mile trace here at this location. That just took, groundwater is traveling on the order of, if days there help me with my memory. I think that's on the order of 1,000 feet per day for groundwater velocities, and the same up in this area. Very high groundwater velocities on the order of 500 to 1,000 feet per day on our 3-mile traces. We have a 32-mile trace that started east of Wendell and is discharging down here at Box Springs. And that's 32-mile distance, and that just took 2 years to travel 32 miles. So groundwater is moving at high rates at numerous locations, and so it'd be interesting to see what age dating shows versus what our groundwater tracing velocities show. That's a very good question.
Thanks.
Hey, Neal, this is Lewis. So on a question, milepost 31 and milepost 28, I think you've done traces there. And also the Wilson Canyon, what are your numbers on those for your miles of travel when you did the traces?
I just noted milepost 31 is 32 miles. Wilson Trace is still in progress, and we don't have results on that one. And we didn't do a trace at milepost 29.
Good. Got one more question in Moscow.
Yeah, I have a question. I'm wondering if there's been any efforts to map recharge zones, looking at like the watershed scale, to map recharge zones to see how like shifting precipitation inputs or long-term patterns are affecting spring discharge.
I believe those efforts are being entertained and active in our modeling committee group, and I would defer that question to them.
Any other questions? And please don't forget to unmute yourself, or you can also type the question in the chat window.
Hi, my name's Neal. I have a question just out of curiosity. Reading into your background, it looked like you had a lot of experience with paleontology research, and I was wondering what steered you toward a career in like hydrology with the Idaho Department of Water Resources instead of paleontology.
Yeah, that's kind of a good question. Basically, what happened is I was studying my master's thesis on perched aquifers that were causing landslides at the Hagerman Fossil Beds National Monument. And so by association, working for the monument, I gained a lot of field experience with paleontology. So I worked for the fossil beds for 11 years. And so that's how that evolved.
Thank you.
Mm-hmm.
There's a question.
Hey, Neal, this is Lewis again. What traces is the IDWR going to do on the upper valley for the recharge?
We've got a number of traces that have been in planning stages, and so we're undergoing those preparations, and it's kind of in flux at the moment, you know, given that we're now in drought situation, but they're forthcoming in our planning stages.
Okay, thanks.
Mm-hmm.
Fantastic. I see that Roy from the USGS sort of added a comment for you.
Let me see if I can find that.
That was in response to the age dating question the person had earlier.
Thank you.
Neal Plummer and Mike Rupert did some age dating in the Magic Valley for part of a NACWA study in the early 2000s, but I'm not sure if they did any dating of the springs themselves, but there is a lot of low-level tritium, and we did do some isotopes on 5 of the springs, or several of the springs, I guess, in some papers in the 90s that could give you relative ages of the different spring water in the area.
Thank you. I really appreciate chiming in.
Any other questions for Neal? All right, well, that doesn't seem to be the case. So thank you so much for a very informative talk. I've learned a lot about the area. So thank you. We will reconvene next week, and we'll talk about water markets next week. So thank you so much, and thank you for participating in the seminar series.
You're welcome. Thank you very much.
Yay.